Have you ever watched a robot arm move and just wondered, how? How does it pick up something fragile without crushing it? Or how does your printer head zip back and forth, landing perfectly every single time? Well, it's not magic. It's all about the art of precision control. Basically, taming a motor's wild power and telling it exactly where to go and, just as importantly, when to stop. Today, we're diving deep into the incredible world of servo systems. All right, so here's our game plan. We're going to start with a basic problem. How do you get something to be precise? Then we'll meet the legendary algorithm that makes it all happen. We'll look at how you tune it, first the old school way, and then with some cool AI. After that, we'll compare two different types of control. And finally, we'll wrap up with why any of this actually matters in our day-to-day lives. So let's start at the very beginning. The core challenge is actually pretty simple to understand. You have a motor that just wants to spin, and your job is to command it to move to one specific spot. And I mean one specific spot, and then just hold perfectly still. Sounds easy, right? Well, it's a bit more complicated than it looks. I mean, really think about it for a second. When you hit print, how does that machine place every single dot of ink so perfectly? Or when a huge CNC machine carves a complex part out of metal, how does it follow that intricate path with like sub-millimeter accuracy? The answer to all of this lies in a concept called position control. You see, position control isn't about just shouting a command and hoping for the best. Nope. It's a dynamic, non-stop conversation. The system is constantly asking itself two questions. Where am I right now? And where am I supposed to be? And then instantly it calculates the difference and makes a correction. And this whole process has a name. It's called a closed-loop feedback system. It all starts with a command, right? That's your target. The controller then tells the motor what to do. But here's the crucial part. A sensor provides a feedback signal, telling the controller where the motor actually is. The system compares the target to the reality, calculates the error, and immediately adjusts its action. This loop runs thousands of times a second. It's a constant cycle of command, act, measure, correct. Okay, so how does the system figure out exactly what correction to make? Well, for something like 90% of all industrial control systems out there, the answer is a legendary, time-tested algorithm known as the PID controller. It's the brain behind the brawn, and it is beautifully powerful. Now, here's the formula that makes the magic happen. And listen, don't let the math scare you. We are not here to solve equations. We're here to understand what's going on. And the secret sauce is right there in those three parts, P, I, and D. You can think of them as a team of three specialists, all working together to guide the motor perfectly. First up is P for proportional. I like to call this one the reactor. It's simple and direct. It looks at the error right now. How far away are we? And applies a corrective force that's proportional to that distance. So if you're really far away, it pushes really hard. As you get closer, it eases up. This is the one that does all the heavy lifting. Next is I for integral. This is the historian. Now, the proportional part is great, but it often leaves a tiny little error. It gets you almost to the target, but not quite. The integral term looks back at this accumulated error over time. It sees that persistent mistake, and it slowly builds up force to get rid of it completely, making sure you land exactly where you're supposed to be. And finally, we have D for derivative, the predictor. This one is all about the future. It looks at how fast the error is changing. So if it sees the motor is screaming towards the target really, really fast, it knows it's probably going to overshoot. So what does it do? It applies the brakes. It dampens the response to make sure you have a nice, smooth arrival without flying right past your destination. So, we've got our team, the reactor, the historian, and the predictor. But, and this is a big but, getting them to work together in perfect harmony, that is a whole other challenge. This process is called tuning. For decades, tuning was a true art form. You needed a skilled engineer to sit there and manually tweak the gain values for P, I, and D. It's an incredibly delicate balance. Too much P and the system just overshoots and oscillates like crazy. Too much D and it gets slow and sluggish. The traditional methods were slow, they relied on a lot of trial and error, and if you got it wrong, your performance was just terrible. But what if we could automate this whole messy process? What if we could use artificial intelligence to find the absolute perfect settings, way faster and more accurately than any human ever could? And this is where a really fascinating field called soft computing comes into play. Basically, it's a bunch of smart computational methods inspired by nature and biology that are amazing at solving really complex problems. And for tuning a PID controller, oh yeah, it's a total game changer. Two of the most popular techniques are actually inspired directly by nature. The first one is a genetic algorithm, or GA. It works just like evolution. It creates a whole population of random PID settings, it tests them, it keeps the fittest ones, and then it breeds them to create a new, even better generation. It does this over and over until it literally evolves the perfect solution. The other one, particle swarm optimization, is inspired by a flock of birds. Each particle is just a set of PID values, and they all fly through the range of possible solutions, sharing information with each other to quickly zero in on the best spot. And you don't just have to take my word for it. The research on this is crystal clear. These AI techniques don't just make tuning faster, they deliver objectively better results. Period. They find a level of performance and optimization that the old school methods just can't touch. And that leads to machines that are way more efficient and precise. Okay, so we've got this incredibly powerful AI-tuned controller. Awesome. But we've really only been talking about one kind of control, getting to a specific place, and that's position control. But that's really only half the story. To get the full picture, we need to compare it with its close cousin, speed control. And the fundamental difference really boils down to the command signal itself. For position control on the left, what the system cares about is the number of pulses it sends to the motor. Each pulse is like a tiny step, so a certain number of pulses equals a total distance. But for speed control on the right, it's all about the frequency of those pulses. How fast you send them determines the motor speed.
So let's just sum it up. Position control, your goal is a specific location. Your command is a set number of pulses, which means distance. And its key feature is something called servo locking. Once it gets there, it holds that position rigidly. On the other hand, speed control, your goal is a specific velocity. Your command is a pulse frequency, which means a rate of speed. And its key feature is maintaining that speed perfectly, even if the load changes, like say a conveyor belt suddenly gets heavier.
So we've covered the problem, the classic PID solution, how AI is making it way better, and the different types of control. But why does any of this really matter? What's the big deal?
Well, because this technology is quite literally everywhere. It's all around you, hiding in plain sight. It's in the robots that build our cars, the machines that print our books. It's in the autofocus system in your camera that snaps that perfectly sharp photo. It's inside the hard drive that's storing this very file, and it's in the gigantic antennas that track satellites way up in orbit. Our entire modern world is built on a foundation of precision motion control. And all of this leads to one final exciting thought. We've seen how AI can tune these systems to a level of performance that was impossible before. So, as this intelligence gets even smarter and our ability to control the physical world gets more and more precise, what's next? What new frontiers in automation, in medicine, in manufacturing, and exploration are we about to unlock? It's a pretty incredible future to think about.
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.